Hello, welcome back. Before we get to series review number 2, before we begin number 6, I want to point out a mistake I made in question number 5. In question number 5, when we get to the geometric series formula, remember it's a times the common ratio to the nth power. But if we look here, we have this negative 1/2 to the third power right there. And that actually kind of changes things a little bit because we should distribute first. In other words, what should happen is that this should become negative 1/8 to the n. And our common ratio is not 1/2, but negative 1/8. So this becomes right here this should become 1 plus 1/8. So that's going to divide it by 9/8 right here. So our common ratio should not have been negative 1/2, but negative 1/8. And if we invert and multiply, we were going to get this negative 1/8 times 8 over 9. And our answer should become negative 1/9. So I apologize for that, but I want to make sure I get that adjusted for you guys first. All right, so let's go ahead and take a look at number 6 right here. Number 6, we're looking for some of a geometric series right here. And we found the first term, which was 9/8. And now we have to come up with what is the common ratio. Well, one way to get the common ratio is to just take the previous term, a sub n plus 1 divided by a sub n. The ratio should be the same. So if I take this negative 3/4, I divide it by 9/8. That's going to give us, if we reduce it, negative 2/3. You can go and verify that if you need to. And then to get the sum, we're just going to use our formula, the first term over 1 minus r. So that gives us 9/8 over 1 plus 2/3. And of course, this is just 9/8 divided by 5/3. And if we invert and multiply times 3/5, we're going to get 27 over 40. And there is our sum. All right, so let's take a look at the next one here. Ready? Number 7. For number 7, we want to find a Taylor polynomial of order 3. So another way to say degree 3, at x equals 0 for the square root of 1 plus x. So let's go ahead and take a look here. So for the first question right here, we are going to take our derivative. So we're going to get 1 plus x to the 1/2. And again, on the AP, they're not going to make it too terribly hard for you for the derivatives here. This is going to give us 1/2, 1 plus x to the negative 1/2. Take the second derivative, that should give us negative 1/4, 1 plus x to the negative 3/2. Now there's a chain rule, but it's just 1, so we don't have to really worry about that if we don't want to. And then the third derivative, we're going to get positive 3/8, 1 plus x to the negative 5/2. And then we're just going to plug in 0. Plug in 0 here, we get 1, 1/2. This becomes negative 1/4, and here we get 3/8. So we can write our Taylor polynomial. So we can go p sub 3 of x is 1 plus 1/2 x minus 1 over 4 times 2 factorial x squared plus 3 over 8 times 3 factorial x cubed. And you can leave it like this. Remember, a polynomial has an equal sign, right? So don't forget about that. We could, if you want to be fancy, write it this way. F of x approximates all of this, if you want. Now, we can reduce this if you need to. This should become 1 plus x over 2 minus x squared over 8, because 2 factorial is 8, plus, what's this going to become? 1 over 16, because 3 over 3 factorial, remember, it's just 1 over 2 factorial right there. So that's just 2, so it becomes 1/16 x cubed, if you want to reduce it. All right, but just remember, if you want to do a Taylor polynomial, we're going to be equal if we write as use p, but the function is just approximates. We should have the squiggly there. All right, so let's take a look at the next example here. All right, so let's take a look at some AP questions here. Number 8. Number 8 says the function f has a Taylor series about x equals 2 that converges for all values of x on the interval of convergence. So chances are they're going to want an interval of convergence here for us today. The nth derivative of f at x equals 2 is given by this. So what they're telling us is the value of the nth derivative. So let's take a look here. So let's go write that out. This is the value of the nth derivative. And if we think Taylor, this is the top part of our Taylor polynomial. They're giving us this top part of it. And they tell us that the first term is just 1. All right, so let's take a look here. So if we want to go ahead and start solving this. So let's see here. So the first question says, write the first 4 terms and the general term of the Taylor series about x equals 2. So let's go ahead and do it. Now they already tell us the value of the first derivative is, zeroth derivative is 2. So let's go ahead and get started. So the first thing we have to do, f 0. Now we don't do too much here because we know f0 of 2 is already 1. So we don't have to really do too much with that one. But let's take a look at 1. If f prime is, if n is 1, if we go up here, plug in a 1, that's going to give us 2 factorial over 3. So this is just 2 factorial over 3. And do the same thing for the second. That's going to give us 3 factorial over 9. And let's see here, the third, this is going to give us our fourth. So let's see here, this is going to become, plug in, this is going to give us our fourth term, which is what we wanted. Plug in a 3, that gives us 4 factorial over 3 cubed, which is 27. So now we can go ahead and generate our Taylor. Part A, let's go ahead and generate our Taylor polynomial now. P3 of x, is the third derivative, first 4 terms, is the following. Nope. Careful, I messed up there. In this case right here, they are saying write the series. Anytime we see a series, don't forget that's our plus ... right there. So this is our Taylor series. So we can say f of x is, our first term is just 1, plus this becomes 2 factorial, which is just 2 over, what's that? 3 times 1 factorial. This just becomes x minus 2 to the first. The next one is plus 3 factorial, which is 6 over 9 times 2 factorial, x minus 2 squared, plus 4 factorial, which is just 24 over 27 times 3 factorial, x minus 2 cubed, plus ... plus, and now I got to write the general term. So to get the general term, I can just really use the top part of this, and that's just going to be this n plus 1 factorial over 3 to the n times n factorial. That comes, and remember, this n factorial here comes from my Taylor, and it's going to be x minus 2 to the n, and plus ... And there's our answer right there. Now we can simplify this if you need to. Of course, if we could also make this just becomes n plus 1 factorial over n factorial. That is just becomes n plus 1 over 3 to the n times n factorial plus ... if you want to simplify that. All right, so that was part A. For part B, let's see here. We want to find the radius and interval of convergence, so we're going to use our general term. I forgot to finish up my general term up here. Let me go and finish it up here. This can become x minus 2 to the n plus ... So what we're going to do now is we are going to write the general term to see if the intervals for its x's will converge. Now you can use the simplified version or the non-simplified version. It'll work out the same. So I'm going to use the simplified version here just to make it easier. Interval and radius of convergence. This is our ratio test, the limit as n goes to infinity. And this is just becomes, oops, I did kind of mess up here again. When these simplify, whoops, sorry, let me fix that, n plus 1. Sorry, when these do simplify, this actually canceled out. Sorry, so just 3 to the n there, 3 over n, 3 to the n on the bottom. So, boy, I'm on fire this morning, huh? So when we simplify this one, we're going to get this n plus 2 over 3 to the n plus 1, invert and multiply, 3 to the n over n plus 1, and gosh, I'm on fire. I wish I knew how to edit videos. All right, so over here, after we have to multiply by this, this is going to become on top, x minus 2 to the n plus 1, and then I'm going to invert and multiply. There we go. 3 to the n over n plus 1 times x minus 2 to the n. That has to be less than 1. So let's go ahead and simplify this. This becomes the limit as n goes to infinity. And let's see, I can't really do anything with the n plus 2 and the n plus 1, so I'm just going to leave those alone, n plus 1. The x to the n plus 1 just becomes x minus 2 on top, and I get a 3 on bottom. That's less than 1. And if I keep, and anything that does not have an x can get factored out. So I can take out this x minus 2 over 3 times the limit as n goes to infinity. And I get this n plus 2 over n plus 1 less than 1. This is 1. So therefore, I just have the absolute value of x minus 2 over 3 is less than 1. So therefore, we get x minus 2. The absolute value is less than 3. So I have the radius. So I have the radius. Whoops, hello. So I have the radius right now. The radius, remember, is just this 3. And now we need to, and I even have the center. The center is just 2 right there. So with the saying, if I were to solve it, if I have my center at 2, I can go up 3 units in either direction. And that's going to put me at -1 and at 5. So now we have to get the interval. So right now the interval looks like it's between -1 and 5. We have to check the endpoints. So let's go and check the endpoints. Don't forget to check the endpoints here. Because remember, the ratio test guarantees convergence if less than 1 and greater than 1 it will diverge, but we have to check out what if it equaled 1. So we just plug this into our series. We're going to put, let me see here. The first endpoint we can check is -1. And if we plug that in, if we plug -1 into our series that we have up here, where's that? There it is. If we plug -1 in, this is going to be -3. So we get n plus 1 over 3 to the n times -3 to the n. And these will cancel, and that's just going to give me a -1 to the n times n plus 1. And if we take this series as we go on forever, if we notice what's going to happen here, this is going to diverge. So if we take the limit as n goes to infinity of n plus 1, that's going to equal infinity. So therefore, this diverges by nth term. So it won't work at -1. And if we try x equals 5, same thing, we're going to get this n plus 1 over 3 to the n, but this time times 3 to the n. And those will cancel out. And again, if we take the limit as n goes to infinity, this is going to become n plus 1, which is infinity. So therefore, again, this diverges by nth term. So neither one of the endpoints will work. So they're our answer. We don't have to put the equal to signs. And let me reread the question because I think this just honestly just said find the radius, not the interval. So you didn't have to find the interval for that one, just the radius, which was 3. So on the AP, you just want this. But we did that for fun anyways. All right, so let's take a look at part C. Now, part C says, let g of x be a function satisfy the following. So g to its 3 and g prime is equal to f of x. Write the first 4 terms of the Taylor series for G. So that's easy. We just want to integrate. So we're just going to integrate this. So we're saying that for part C, that, well, G of X is just the antiderivative of what we found for F. This 1 plus 2 x minus 2 over 3 plus, what was the next one here? I'm going to simplify this. This time, if we simplify 6 over 9 times 2 factorial, this becomes, what's that? 2 over 3 times 2 factorial. So we get 2 over 3 times 2 factorial, x minus 2 squared. And the next one would be, if we were to simplify the next one, this is 9 over, oops, sorry, there we go, 24 over 27. This becomes, if we reduce that, we would get 3 over 3 squared times x minus 2 squared plus dot 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 dx. And if we would integrate this now, we would just get x plus 2 over 3. This becomes x minus 2 squared times 2 plus this over here, we're going to get 2 over, hold on here. You know, I keep messing this up. There we go. 2 over 3. There, that term is gone. There we go. And let's see here. X minus 2, 3 over 3 squared. Yep. So I will need one more term up here. I kind of messed up my simplification over here. Our next term here, on top here, this will become 4 over 3 cubed, x minus 2 cubed plus dot 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 dx. So you can simplify that. So we take the derivative here, we get 2 over 3 squared, and this becomes x minus 2 cubed over 3. Again, I keep messing this up. So that was a 3 right there. There we go. There we go. That was a 3 right there. And then the next one, 4 over 3 cubed, you know what, times, what do we get here? This becomes x minus 2 to the 4th over 4 plus dot dot dot, and at the very end plus c. I think I'm done with this problem after this one. All right, now we have to find c. To find c, they gave us the initial condition. G of 2 was 3. I just plug it in. G of 2 is 3, so I go 3 equals, and this is going to become 2 plus. Now, of course, if I plug in 2 for all the other terms, here, they all just become zeros. So I get an infinite number of zeros. So I can go plus 0, plus 0, plus 0, forever, ever, ever, plus c. So therefore, c is just going to become 1 if I bring that 2 over. So g of x would just equal 1, or you can do 1, put the c first, or you can put the c last. It doesn't matter. I'll put the c last because that's what I have up here. We would get x plus 2 over, which that just becomes 2 times 3, x minus 2 squared. And you can reduce it if you want to. 3 squared times 3, x minus 2 cubed plus 4 over 3 cubed times 4, x minus 2 to the 4th plus dot dot dot, plus at the very end 1. All right, and there's our answer. Oh, boy, I apologize for that. I know I kept making that mistake right there. All right, and there's one more part for this one, part D. Part D says, does the Taylor series converge at x equals negative 2? And, well, now they're asking for the interval. Well, luckily we already found the interval. The interval was between negative 1, not including negative 1, and 5. So the answer is no. X equals negative 2 is outside the interval of convergence. All right. I'll make another video, maybe take a look at this one again, especially that part C right there. So I know I kind of messed up on that one. But going to my next video, we can take a look at question number, the last question right here, okay? See you then.